Welcome to our Thursday webinar. The first thing that we'll look at is to have a very brief overview of the confusion matrix. The second thing will be to look at scaling or renormalization, normalization, and finally we'll look at permutation test scoring as a sort of an advanced means of guaranteeing that the machine learning in our classification context is doing well. So we've done some introduction, some basic machine learning with classification. You have seen how to prepare the data, how to train a model, how to withhold some labels, and then sort of test your model scoring on the withheld test data and find out if you have achieved a good classification or no. Now, in this lesson here, the one that we are dealing with today, there are further topics. The sort of said, well, it's basically very easy to say fit and predict, right? It's basically what we needed. Fit the model, predict some values. Now you can do a little bit more once you look into the details of how this works. There are a couple of things that need special attention. There are also ways to view whether things go right and wrong that vary from case to case. And let's start by having a quick look at this Wikipedia entry only about the confusion matrix. So if you have done the lesson materials, you saw that there is a function that actually takes your input and converts it into a nice display, or nice, I don't know if it's nice, but into a display of the confusion matrix. And if you run various classifiers, you can have multiple matrices plotting next to each other, which gives you actually a nice overview, which is a nice summary of the performance of multiple classifiers. Now, what is the confusion matrix? Have a look at the Wikipedia entry, it's quite good. It tells you much more than I want to say, but I just want to highlight that it's a well-known concept. It's nothing new, it's an old thing that actually has also been known under error matrix or under some other name like matching matrix, which it says down here. And in the way that we use it, actually what it needs is these two sets of labels, that is the true labels and the predicted labels, and it's nothing but plotting the scores for each in a square or coloring it. Either you can use numbers or colors, it's up to you, and then give you an overview of the result of one statistical testing that you have done on your data. So here we have the true and the predicted, and we then compare whether the things were right and wrong. One thing why I mention this Wikipedia page is because you can look up all those sometimes not quite straightforward definitions of all the scoring terminology that is around in the literature. And then depending on from which field you come from, you might be used to one but not to the other. So there's also a bit of a help with that sometimes two names are given to the same score, like precision is also known as PPV or positive predictive value. And if you come from medicine, certainly sensitivity and specificity are what you have probably learned, but you might not know that in other fields the same thing is called recall and selectivity or true negative rate. So it's a nice overview of how you get all the values from that same square that will somehow put into our confusion matrix. Everything can be done. And another thing to recommend in that Wikipedia article is that it does a walkthrough of that, how to set this thing up by example of some invented thing here, a couple of numbers. So it says you're given a sample of 12 pictures, 8 dogs and 4 dogs and 8 cats and so on. And then you see something that looks suspiciously like a list in Python, so you can copy and paste it if you want to program it. And you see you have actual or true versus predicted. And of course you then can compare those two. Maybe you remember how you can compare those arrays directly to see how much overlap they have. You can calculate what percentage is overlap, what percentage is true, not true, and so on. But then it derives the confusion matrix here sort of manually, verbally, just by putting in those numbers into a table where I say true and predicted, and you see that you have cats and dogs on both. Of course, it must be symmetric, and then put in the numbers. And just below it says true positive, true negative. So there's a true diagonal, if you like, the one that in our plot we want to be as dark as possible. And there's the wrong diagonal, the false negative, false positive diagonal, where you want it to be as white as possible. And that's basically it, right? So you can have a color view also here. That's the same color view that we're doing. Here's our confusion matrix. I don't know if you have difficulties distinguishing red and green, maybe it's not so obvious, but if you program it, then you can create your own background and color using imshow. If you remember imshow, you can make that same square matrix nicely colored in the way that you like it to be. I think that's basically it. The main feature that we need to remember when we apply to our classification task, that this confusion matrix and the way it works, and also the plot, the function that you have there in the materials works, is that it only works with 2 labels. So it's true and false, 1 or 0, whatever you like, but it will not work with more. Wikipedia also doesn't go much farther, but gives you at least an example. Where is it? Here's the example of a sort of a confusion matrix with more than 2 labels. And of course it gets more complicated then, but that's not where you can use our code to work with. So you would have to then expand your own code or read up on the literature. And as you can see, of course, more labels means it's a bigger matrix than 2 by 2. It's in this case a vowel matrix or 5 by 5 matrix. But otherwise you have the same, the fully true on the true diagonal, and then the off diagonal matrices tell you then how you went wrong, but also in which direction you went wrong. Right, so there's something that we don't need because it's either true or false. There's no other possibility. But if you are wrong with the prediction of O, there are 2 possibilities. You can confuse the true O with an A and predict A where it should have been O, or you can predict a U. In this case here, 3 false in that a U was predicted where actually an O was expected. And so you can have a more differentiated view, and you can see also from the off-diagonal elements, you can learn something. You can learn in which way did the algorithm go wrong and make that some feature to improve your model if you want that. Yeah, that's about it. Just to say this is a simple summary of the classification that we have done anyway. It's just a way of looking at the results. And if you want, of course, you extract sensitivity, specificity, or whatever you like for your specific purpose out of the data. Okay, let's take this away. And our second piece now will be an actual coding exercise. So there's a little bit of code that I have prepared. I did put the code on the Moodle course website, but I only put it like an hour ago or so. So if you haven't seen it there earlier this morning, maybe you can actually download it, but it's nothing very important there. Just for reference, if you want, you can download it and check it and tell me if something was wrong, of course. So here's that problem about normalization or scaling. I'm using the words interchangeably, but there are some slight differences which you can look up if you're interested. So first of all, we are dealing with preparation of data before we go into the machine learning. And if you have done the course code, you saw it that we can compare sort of the data as they are, the raw data, with one specific normalized version and see. And maybe also notice that sometimes it can make a difference, sometimes it doesn't make a difference, sometimes the outcome is even poorer when you use the normalized data. So there is no general rule about which of the scalings to use or when to use, but you will have to think about it. So for that purpose, it's good to know what are they actually doing to my data. And yeah, let's have a look at 3 of them. So they all come from sklearn preprocessing, and you would typically always use them to make a different version of your data, which you then call scaled or normalized, and you take it along the raw data and see what changes they make under your specific workflow, classifier, evaluation, and so on. I know it can't be predicted. You have to actually do it to see how it works and whether it improves something. Right, so we do the standard scalar, the normalizer, the one that was in the materials, and the min-max scalar, just to see 3 important examples and at least to have an idea what is out there and what is of the most frequent things being done in the community. So we'll just prepare a couple of data and then see what the normalization or scaling does to those data and try to understand how the normalizer works and how you get them out of it. It's all standardized. So the nice thing about Scikit-learn, all those things, even though they come from different ways and you do different things in the background, the way you use the functions, very standardized form. It's always once you know one, you can also use the others to a good extent. So when I started in that script, I'm just looking at the script that I have given you for download with creating some data. So some data, and we use a list to create them. We can use lists, and if we want to put something that somehow reminds us of our data frame, so our features and samples, or columns and rows, if you like, we put in pairs of numbers. And I have 4 pairs, so I might just as well put 4 here. So this is a nested array, a nested list, and I give us 4 pairs of numbers, like first pair looks 1 and 4. Just use the same as here, 3, 1, or whatever it is, 4, 4, and 2, 3. Very arbitrary numbers. And you can see the arrangement is such that we can interpret this as a data set with 2 features. So every pair has 2 numbers in it, so these are the 2 features. And we have 4 pairs, so these are our 4 samples. At least that's how I imagine it. And we can use that as a list, but typically when we do Scikit-learn, it might be good to convert that to an array. That means convert it to a NumPy array directly, just using that function array. And if I have imported as I have, then some data will just be of type array. So then we have our data set. This is our sum data. And we can then go forward and try to scale them. So the way to use a scalar we have imported, let's use the standard scalar first. Standard scalar is a class. a Python class, so you may remember that then we have to instantiate that class. Standard, see if it comes up, it autocompletes, so standard scalar, open close parentheses, no further arguments for our purpose. Give it a name, standard scalar from Scikit-learn, I think is what it stands for. And this will just be our instantiation, so nothing happening. There's just like we say CLV equals random forest and so on. So this is our instantiation, and then we can use it. And we use it by calling its name, of course. And then we use a method that works within that class. So and what we can do for convenience, very simple thing, is we can use fit transform. Fit transform means you fit the scalar to the data and then you transform the data in one go and return the normalized or scaled data. Right? So what we will get out of it, go back to my parentheses. If we are within the parentheses, we need to give an argument, but the argument in this case will of course be the data. So some data is what we want to fit the scalar to and transform into new data, and we then need to call them something data scaled or something. Data scale, data norm, yeah, it doesn't really matter what we do. Well, maybe I should be consistent. Data were called some data, so let's keep that name some data and say some data scaled or normed. And if I use the word normed, then I can later on just copy paste the code. So let's have a look. So I took some data, I fit and transform them with our instantiated scalar, and I get a new set of data, which is of course same size as the old data, but values may differ. And let's have a look. Let's just see what's going on here. Okay, what's going on here by saying print, and then print some data normed. This is not defined. Well, I haven't even run the code, and here I have it, so I don't need to make an extra print function. So this is of course only useful. What I want you to do is print some data, but compare them to the original data. So we have on top, we have the original data, those 4 pairs, 1 4 that I put in, and then the standard scalar has converted them to something new. So of course now is the question, what actually did that scaling do? The standard scale, if you look it up, there's a documentation on Scikit-learn. It removes the mean and it scales to unit variance. So that's why standard scalar, that's something that's a very standard procedure, very often done in data science, and so something that you are probably also, that you have run across, but that is very often used and also highly recommended in many applications of machine learning. So remove the mean means that the output data, the scaled data, will be of mean 0. And you can test it by just calculating the mean of both features, and you will see both features should just have a mean which is somewhere around 0. And of course with 4 numbers it may not be very perfect, but as good as you can get it numerically it will be. And the standard deviation of this, well, extremely small distribution will be fit to 1. Standard deviation is equal to variance in this case. And this means you will have distributions of data that are comparable now for all features in your data frame. Right? Every column will be done by this. The normalization is independently done for each feature. So no, don't worry, it's not confusing one with the other. It's just independently done, but it gives you the same sort of data set where every distribution is on the same scale at least. Hence scaling. Right, okay, and then hopefully I have taken a good nomenclature. And then we don't need this original code here. I just plot these things with copied and paste code where some data and some data are normed. But I call it like this, some data and data norm, such that we can look at them. So we get a figure out of this where you can see some data. This was my values with 3, 1 and 2, 3 and 1, 4 and 4, 4. And you can see after scaling to 0, mean and variance 1 or standard deviation 1, we find values that are all somewhere around 0 and not much farther than 1.5 or so away, not more, typically not more than 2 standard deviations away from that central distribution around 0. So that's what the standard scalar does. Right, so we have instantiated it, used it to fit and transform, and then seen what the resulting data look like. Easy workflow. A nice feature is now you have the standard scalar trained, so to speak, or fitted. Now you can of course use it for any data that you like. Specifically, if somehow now you get more data from that same distribution, hopefully, so say from that same experiment you get more data out of it, you can directly apply that to use the standard scalar SKL, but in this case you don't need to fit again because you have already fitted. You can just directly use transform. So as a simple example, I just put in some list. But you remember the original data were a nested list, so I have to be careful and also do a nested list here. But if I give some new value, 2.3, then it will also give me how these data scale according to that previously fitted transformation, right? So, and that of course can be any number. You can put in 100 samples if you like, and they will be all scaled according to that previously given normalization. So that's like your predict thing, so to speak. You give new values and it will use the old scalar to do the transformation in the same way. So fit transform to do both, to adjust the scalar and give you an output, and transform only to just get new output with that originally trained scalar. Okay, see another example, and another example can be the normalizer. So let's do the normalizer on the same data. Let's say norm SKL. So that's now a new instance of class normalizer. This one called normalizer without further ado, and we apply that in the exact same way. We then, once we have it instantiated, we do fit transform on our data, which was called some data, and we get out of this some data normed. Just call it the same thing, then I can use the same visualization as above. So now first should of course immediately say what is that doing? So what is normalization doing? So normalizer is a scalar that converts data to unit norm. And the unit norm, that's the one that we have in the material, so you can also read it up there, that sort of put all the data. So if you think of a two-dimensional state space like we always have for our scatter plots, and data are distributed all around the place, and what it does, it puts all the data on one circle, the unit circle, so to speak, and that sort of norm, where the word norm comes from, or normalizing, put it all on a unit circle, so to have them nicely distributed on a circle in 2D, if it's 3D, a sphere, in 4D, a hypersphere, and so on. And the unit norm. The unit refers to the radius of that circle, so that's the length of the vector. So the vector can go around the origin, circle around the origin will reach each data point, but the length of the vector will just be 1 because it's the unit circle. So that's the unit 1 circle norm. And it works in the same way. I just try to copy and paste the visualization from above. And for some reason it doesn't. I have to, okay, just stop the code. See, I have not instantiated the figure. I know, so fig x, fig, x equals subplots. I need to create a figure, otherwise I will not see it. And then there's something wrong. It's not subscriptable. Why is that? X, oh, I've given this thing here. So I need to just copy the whole code. Sorry, I've forgotten something. I've forgotten to paste this feature where I create 2 columns for my figure. Otherwise, of course, it will not work. I have now created 1 figure, but I have referred to 2 subplots in that figure. That will not work. So in this case, now the result is actually not so bad, but we might adjust the fig size a little bit. Fig size equal tuple, say 8,8, and maybe more. 12,8, so it's too big. 8 and 4. Okay, so that's nicer. So if you look at the scales, then you can see now the previous data between 1 and 4. So they have now been rescaled, but because they are all positive, all remain in the positive quadrant. And in addition, they now are put on this unit circle, which you can already guess, although it's only 4 points here, that goes from 1 on the x-axis to 1 on the y-axis, and all data are nicely aligned there. So that, of course, that is some distortion to the original data, right? So it's nice for the classifiers and for the machine learning models to work with, because now everything is nicely on that sphere or circle aligned, but of course it distorts the data somehow. It makes a difference to how far you are away from the origin. And that, of course, has to do with, creates a bit of a problem or a question for you, namely, is that allowed? Is there any significance in the fact that data have different sizes, different spreads, or different distributions? Right? So this is something that only you can answer, and you have to test and see what happens to it. Specifically, the question is any information lost by putting them all on a unit circle. And similarly, like you like we had it before, you can now use new data and just transform, get the values for all of those data on this same unit circle with the classifier that you have trained before. So you wouldn't do that if you suspect somehow that something has changed in your experiments or in the way the data were created. If the distribution is suspected to have changed, you wouldn't use a pre-fit transformer, but you would include the new data and fit transform again. Means use all available data to fit and only then transform. Okay, last example. Just very quickly, that was the uniform. That's something that people often like very much, and that I also use. That's the min-max scalar. So the min-max scalar transforms each of the features, again independently of each other, by scaling each to a given range. And to a given range means by default what you get is 0 to 1. So everything that you have will be squeezed between 0 and 1. And min-max tells you already that the smallest value in your data set will be pushed to 0, and the largest values will be pushed to 1, and then everything else according to their correct proportion in between. So let's see how it works. Min-max scalar, it's the min-max scalar, just used to it. What you will get is some min-max SKL, so you have your instantiation, and then min-max SKL you can use on some data to create some data normed. Right? Some data normed obtained from min-max scalar applied to some data. Okay, next trial, see if I can now get the visualization properly complete and with figure creation into the same thing. So still not, min-max scalar is not callable. So where did I go wrong? Is it not instantiated? It is instantiated. That's imported here. Now debugging min-max SKL. Just take the code out, and it's callable. Yes. Some data norm, it can't be used on some data. Why not? Well, I didn't want to call it. What I wanted to do was, of course, what I wanted to use is call a method, right? And the method was called fit transform. Yeah, can happen. So I wanted to use a method on that scalar, and it's fit transform, open closed parentheses, and then apply that to some data. So that now works. That's debugged. Take the code out, see if the commenting out, and see what happens to this set of data. So what we get is the original data, which we know by now, and we now have everything scaled with default settings to a range between 0 and 1 on both features. And if you have 20 features will be all data points between 0 and 1. So you squeeze them to something that is sort of predictable, in the sense that many of the optimization algorithms in scikit-learn specifically, but I think throughout the machine learning community, they expect you to give somehow data that are in this range, because that's how the optimization was worked out to be most efficient. So specifically, classifiers like support vector machines with different basis functions may have trouble if you, given basis functions, you make some assumptions about how they work, and they may have trouble dealing with data where on the one hand you have something between 0 and 1, and on the other hand you have something between 4,000 and 7,000. And it will not be able to handle them easily, because it was all trained to do work with values that are somewhere between 0 and 1, or maybe between -10 and 10, but not many much farther away than that. So at least not orders of magnitude away from those values. And of course, you know that this problem specifically comes when you have heterogeneous data. Right? When you have homogeneous data, they're all from the same output, like proteomics. You have the concentrations of proteins, and they're all within a certain range between 0 and some maximal value, and there might be more abundance or less, but somehow will all be very similar. Whereas in comparison, if you have data from different sources, there can be numbers like 10,000s or numbers like 0.0 and so on, and that will go badly down with some of the classifiers. So here you bring them in the same range between 0 and 1, and in a sense, min-max, you can see it also here on the feature 1 on the horizontal axis. The minimum is brought to 0 and the maximum brought to 1, and the same on the vertical axis, minimum to 0, maximum to 1, and then this one point in between. And of course you can repeat that with thousands of values, and you will see they will all fill that square in the middle. Same prediction, I think, should work as well. Minmax, let's try minmax scale dot, just using the transform, you can put in, so in this case, an array of same dimensions, but new values 4.3, so something that's within 2.3 and 3.7. So put in a value and will be scaled to values between 0 and 1, of course. What it cannot really deal with if you suddenly have a value that is larger than the previous value, because now you predict using the trained scalar, and so it gives you a value 1.9 that is no longer between 0 and 1, of course, because the new value is outside of the original range. So in this case, you would take this data point to the above, rescale the scalar, and then continue to work with that newly scaled version. Right? Okay, so if any immediate questions, maybe no, but now you can see there's a range of things that you can do. You can read up more which one is useful or not, but you have, the best thing is to work with them, to gain experience, and by seeing what happens to them. And yeah, one thing that I might mention is, of course, something like this destroys some information, like a certain information of distribution or differences in distribution is destroyed. So you might not want to do this, specifically if there are data where the size, the relative size matters. So I work on EEG, on human brain potentials, and there, from the size of a signal, like the voltage, you try to infer how close you are to the source of that signal. Right? If you are close, the size is large, so you have large numbers. If you are farther away, you have the same signal but smaller. So size matters, or amplitude matters. So in that case, of course, we don't remove it, we don't rescale it, because we lose information which we think is actually valuable to interpret the data. So this is just some consideration, and there might be others. But it's always worth a try, and if you have a code, it's very easy. Use these 2 lines of code to fit, normalize your data, and run your machine learning model along, and just compare the outcomes and see which one performs better, and then decide whether you want to go with one version or the other. Good. Close, new notebook. Next topic, a final topic for today, is the permutation score or permutation test score. So this is now something where even with the very simple code I made small errors, right? Now I will copy and paste, and hopefully everything will go right. We copied and pasted code is too much to code for you, and I will only comment on a very few features in the code that maybe are interesting. So first we need to import things, and because we want to run a couple of classifiers along each other, I import just as we did in the original material in the class, 8 classifiers, and you have seen it in the class materials, but here the comment, they are put in a dictionary. Have you looked at how a dictionary works? It's this curly brackets, open and closed, and then dictionary needs key and value. So the key is some name that I give to the classifier, of course, indicative name like random forest or decision tree. You can change it. Multi-layer perceptron is a neural network. So whatever you like to give it, they are just for you to remember and to have titles to the figures, as we see later. And then you take the function or that class from the Scikit-learn library, and you initiate it or instantiate it later on with a certain random state. So this is not doing anything. This is just putting this piece of code, so to speak, this instantiation as a value of a dictionary, but by calling that value, you can actually sort of run it, right? You can call that classifier as a value from that dictionary just by getting it from the dictionary. And that's how we can do very convenient manipulation and see a couple of things at the same time, which otherwise is a long, tedious coding. Make circles, I use that's from the material, so nothing new here. I use a data set with two features, if you remember, two classes also, red and blue, and it's an inner circle and an outer circle, and I have started it such that with some default values I have 100 samples, so 100 pairs of values, and I have a factor which is fixed, and I have a noise level, yes, but a certain low noise level, which I consider low. Low in the sense that the circles are quite nicely distributed from visual impression at least. And remember, if you want to have the same thing in a different distribution, just change random state that number here, then you will get a different sample that has the same features otherwise. Right, then the code for the permutation test score. Before I copy and paste it, I want us to have a look at the data set, which is here, and to briefly discuss what we actually want to do. So we have two features, that's why we use the plane to plot them, and we have two classes, that's why we use two colors to color them in. Now what we can see visually now, our sort of visual classification tells us, the red ones are on the inner circle or internally, and the blue ones are on the outer circle, so there's kind of a separation there. And that means we have this topological idea of a circle, a circular distribution, and we connect the way these data are distributed by looking at the colors. How do they fit within that circular symmetry? And when we say inner, that's like small radius for any of the red points or large radius for any of the blue points. And so it means whenever I have a label, red or blue, it somehow correlates with the radius, right? So red, small radius, blue, large radius. And so you can actually, mentally, you can very simply classify by saying, well, I use a circle with a variable radius, and if you did the webinar with me 2 weeks ago where we tried to fit a line to separate the blue and the red, this is the same here, except we use a circle instead of a straight line. So visually it's easy to do, and we can immediately think of what it means. What it means is that the label is directly related to that one feature, radius. Right? Radius is something new that I have inferred from visually looking at the data. Of course I have created, but visually inferred. But it's something that the machine learning model needs to learn. But it's something that can be done. And now we want to say, well, if there's an association of the label with the radius, like red small and blue large, what happens if we destroy this association? Right? If we just take labels that we create, if we arbitrarily assign labels to that data set, removing those true labels and put in arbitrary values, what will happen? Well, the outcome will be, of course, that there's no more association between color and radius, or red and blue will be just mixed all over the place. And what can the poor machine learning model do with such data? Well, it can try very hard to optimize and try to still very hard to predict something, and it will certainly do its best. Right? So there's an implicit danger. Machine learning models are all optimizers. So they always try to get the optimal prediction. That means always above chance prediction if possible. And so if you see some value in the scoring, accuracy, recall, whatever you use, then you might think that's nice, I have some predictive value in that model, but it might also be there just by chance or by happenstance and not really be true, because an optimizer will just find a way to give you some good result based on the data that you gave it. So when we associate randomly labels with the data that have no correlation, where we know there's no relationship because we have done it blindly, then of course we know what our reference point is. Namely, there's a data set where the algorithm cannot predict at all because there isn't anything to predict. And that's the idea of the permutation test score. What we do is we create a test statistic that we know is unable to predict anything meaningful, and we look at how that compares to our test statistic that is from the original data with original labels and see if we can find a difference between the two. So permutation test is nothing but formulating a null hypothesis, like in any basic statistical testing. A null hypothesis, and a null hypothesis is the trained classifier cannot predict anything above chance level. It just can use a coin toss with binary classes, and that's it. And then we can do different realizations of those, because the random assignment of labels can be done in many ways, so you can do a couple of times. And then we create a test statistic or a null hypothesis statistic that we can then use as our ground. And we then look at the true value, the one that is obtained with our actual correlated data or data that have correlated labels, and see whether you are outside of the test statistics. So if I take that code, bring it over here, let me just run the code. So it's the one from the material, so you have probably seen it, and it takes a while to run it. So I already clicked go. There's some scoring there and some values. Let's have a look once it's finished, see how far it goes. I have used data as capital X, as we know, features and samples, Y as the labels, which we conveniently get from our make circles function, and hopefully it doesn't take too long. Shouldn't be too many points. How many points was it? 100 points, so shouldn't be too much trouble to get this. So the first feature that I want to show you, I have said I can do various realizations of my null hypothesis, and the number of realizations or number of permutations is given here. So there's a keyword argument, which is n permutation, n subpermutations, and I have set this to 20, so I've said do 20 times assign random labels to the data, so uncorrelated, and then run your model training, give me the accuracy, and tell me what you get. And 20 means I get a distribution of 20 values. I can create a histogram of those 20 null hypothesis generated outcomes of the statistic, and you can see the blue are the histograms of those null hypotheses. So the blue are the distributions of the null hypothesis, and with that red line, which is just the chance level, so the 50% where you predict that chance, that is sort of the expected mean value for a chance prediction. And of course, because the optimizer tries to do something better, and sometimes it's above, sometimes it's below. And you can see those distributions quite nicely. And then your actual training and outcome from the correlated data, from the data with the true label, so the one that we had originally, is in green. So I hope that's visually perceptible here. Green value then showing the scoring that was obtained with the same classifier, now with the correct data. And what you want to see is that this green line is as far as possible away from the blue distribution, right? So if in one instance, like here, you find the green value below chance level, so you are worse than chance, better use chance, and you are within the distribution, then you can see, don't trust this classifier, this is not a good outcome. Of course, you have probably seen why that support vector classifier fails. In this case, it uses linear basis function, and so it will not work. But just as an example how all the classifiers except for this one do a very good job here. And just have it repeated slightly, maybe take now 30 permutations, but do a much harder task by increasing that noise level to 0.5. So let's just do that, see how the data are distributed. Now you can see it's not so trivial anymore, right? The high noise level now, radius is not very much of a clear predictor anymore because radii are mixed, and of course a much harder task for the classifier to do, which I run in the background. So you can in the meantime already start to think what will it look like. So we have an hypothesis that this data cannot predict it above chance level. Null hypothesis, I will create a distribution around it, and then we'll do our proper training with the original data, but you can see it was very hard to do visually. And of course, two features, this is all we have. There is no other hidden dimensions where we might exploit and you do some beneficial search from. There is nothing else there, so all we can hope for is some a chance success, so to speak. And we'll have a look in a moment what the distribution looks like. And I've increased it slightly to 30 just to get the distributions a little bit nicer to see, and otherwise it will be the same output. So here's our output, and you can see the distribution, the histogram plotted in blue, and in contrast to what we had before with this high noise level in our synthetically created data, each and all of the classifiers fails to do anything useful in the sense of we are outside of the distribution. And you can see now why it is important to do a permutation test, because you have something like this here. The radial basis function did a sort of a good job in the sense that red curve, chance, and best fit green are somehow separated, and it looks like, yeah, they are fairly good separated. Well, they aren't. They are 0.1 apart, which is very little, because there isn't anything that goes above 0.7. We don't have a histogram like before that goes up to 1, but only to 0.7. So all values are less than 70% in that specific scoring. And that means that now, or even though in a single instance you might well have a chance level that is 50% and here a level that is 60-something% or so in the classifier, but it doesn't mean anything because you look at the distribution, and if you use the default values of the function, which is permutation test score, then you will see a better, more nicely filled distribution, but it takes 100. It's 3 times as much effort to do this, but if you do a nice distribution, then you will see that this green value is actually not to be trusted because it falls at the tail of that distribution and as such very unlikely to be a good prediction. Okay, then let's stop this with a small comment, something that I just want to point out while we have a minute left, and that is the for loop, right? Have you seen the for loop, how the for loop works? The for loop here says take a couple of things out from a very complicated term, and that uses a couple of things. So I just wanted to point you to it. The classifiers, you know, right? You know classifiers, and because they are dictionary, when you say items, you take both the keys and the values. So you have the name of the classifier and you have the classifier. In addition, you want to plot them on 8 different plots, so you have different axes that you want to sort of prepare for the plot to go in, right? Our fig axis is equal subplots. So this is done here by creating an array from as many axes as you want to have plotted, put them together with the classifier, say 1 axis for each classifier. That's the zip function, sort of concatenate, put them together, and then make them subject to an extraction where you get out of them the axes one by one in the for loop. So the axis is here called axis. It's got from the collection of axes, so that you prepare, you have 8 axes, 4 by 2, 4 columns and 2 rows, you get 8 axes, and then you will get them one by one for each classifier 1, because with every axis you also get a specific classifier, starting with random forest, and you get the corresponding sort of instruction to take that classifier and use it for classification. And if you do it, you can now run the code, get your test statistic, and you can very well estimate whether that's good or bad. And finally, if you want to have that quantitatively, of course, it's a null hypothesis, and you have a test statistic that you want to compare whether it's compatible with the null hypothesis or whether it rejects the null hypothesis. Calculate the p-value, just get the p-value, and then you have one way of saying this is good or this is bad. Warning, of course, you can p-hack this, because the more permutations to do, the more sure you are to get a small p-value, so be very careful. Don't trust in the p-value, just use it ever as a rough estimate, like we did here visually. Say, well, that's more probably within distribution, outside distribution. Use it roughly and with care. Don't try to overdo things by using many permutations. It's no use, especially if you have 100 points. How many permutations will be sensible in any case? And you remember the default was 100, so that's why if you don't specify this keyword, it might take some time to do the calculation. So that's the end basically of our classification introduction in 3 lessons. You see how it goes, you see how it can better scorings and how you can improve it. If you now trust one of those classifiers and you have good achievements, then you can also think, now I want to go further and do the hyperparameter adjustment to further improve it. But look at what it says about leaking, and especially the website also mentions an article that you can look into it. Take a look at that article, even though it talks about rehabilitation treatment in the beginning. The end is very much focused on the kind of discussion that is generic in the sense that we are doing here in the course. Thank you very much for watching to the end. Wish you good working, and if you like, see you again in 2 weeks, and we'll then go into unsupervised learning.